Before we begin, imagine stepping outside on a clear night. The air is still. The stars seem quiet and unchanging, scattered across the darkness as they have been for countless generations. To our eyes, they appear timeless. Yet every point of light carries a story that began long before human civilization, long before Earth itself was fully formed. The light reaching us tonight has traveled unimaginable distances, crossing oceans of space for years, centuries, millions, or even billions of years. For thousands of years, people looked upward with wonder. Ancient astronomers mapped the constellations. Sailors crossed oceans by following the stars. Philosophers asked whether the heavens were eternal. Every generation built larger telescopes, hoping to see just a little farther than the one before. Each new instrument expanded humanity's horizon. Then came a telescope unlike any ever built. Its name is the James Webb Space Telescope. Unlike the familiar observatories resting atop mountains, Webb was never meant to remain on Earth. Even the clearest atmosphere blurs faint infrared light. Our planet itself radiates heat, masking the delicate signals arriving from the earliest moments of cosmic history. To truly look into the ancient universe, astronomers needed a telescope that could leave Earth behind entirely. The dream began decades before Webb ever launched. Scientists envisioned an observatory capable of detecting light so ancient that it had stretched far beyond the visible colors our eyes can perceive. As the universe expands, the light from distant galaxies is stretched into longer wavelengths through a process known as cosmological redshift. Galaxies that once shone brightly in visible light now appear primarily in infrared. To observe the universe's earliest chapters, humanity first had to learn to see the invisible. This challenge demanded extraordinary engineering. Rather than constructing a single enormous mirror, engineers designed 18 hexagonal mirror segments that would work together as one perfectly aligned surface. Each segment was carefully shaped from lightweight beryllium, chosen because it remains remarkably stable even at extremely cold temperatures. The mirror itself spans approximately 6.5 meters across, making it more than 6 times larger in collecting area than the mirror aboard the Hubble Space Telescope. Its golden appearance is not simply decorative. Each mirror segment is coated with an extremely thin layer of gold, only a fraction of a human hair in thickness. Gold reflects infrared light exceptionally well, allowing Webb to gather the faintest whispers of ancient starlight. Even so, the mirror alone could never accomplish its mission. Infrared astronomy faces an unusual problem. Anything with warmth emits infrared radiation. People do. The Earth does. The Moon does. Even the telescope itself produces heat. If Webb became even moderately warm, its own glow would overwhelm the ancient signals it hoped to detect. To prevent this, engineers created one of the most remarkable structures ever sent into space, a 5-layer sun shield. Each layer is thinner than a human hair, yet together they span roughly the size of a tennis court. Working together, these layers continuously block sunlight from reaching the telescope's scientific instruments. On the sun-facing side, temperatures can exceed 100 degrees Celsius. On the opposite side, where the mirrors and instruments reside, temperatures plunge below -200 degrees Celsius. This extraordinary difference allows Webb to operate in near-perfect darkness and cold, conditions essential for detecting the oldest infrared light in existence. The telescope would also need a home, unlike any previous observatory. Rather than orbiting Earth like Hubble, Webb would travel nearly 1.5 million kilometers away to a location known as the second Lagrange point, or simply L2. At this special region of space, the combined gravitational pull of Earth and the Sun allows a spacecraft to orbit while remaining in nearly the same relative position to our planet. From L2, Earth, the Moon, and the Sun all remain on the same side of the spacecraft. This allows the sun shield to block their combined heat continuously while the telescope gazes outward into the deep universe. It is a remarkably quiet location, far from Earth's reflected light, far from atmospheric interference, far from unnecessary heat. almost perfectly suited for listening to the oldest light still traveling across creation. Reaching this destination, however, was only the beginning. Unlike most spacecraft, Webb could not fit inside the launch vehicle in its final form. Its mirror had to be folded, its sunshield had to be folded, its supporting structures had to be folded. After launch, the telescope would perform one of the most complex deployment sequences ever attempted in space. More than 300 individual mechanisms had to operate successfully. Hundreds of potential points of failure existed. Engineers had spent years testing every hinge, every cable, every motor, every latch. Still, once Webb left Earth, there would be no astronauts available to repair it. Every deployment had to succeed the first time. On December 25, 2021, an Ariane 5 rocket lifted gently from French Guiana, carrying the hopes of thousands of scientists, engineers, technicians, and dreamers who had devoted decades of their lives to this remarkable project. The launch itself lasted only minutes. The journey afterward unfolded over nearly a month. Slowly, almost gracefully, the telescope began awakening. Solar panels unfolded, communication antennas extended, the enormous sunshield stretched outward, its delicate membranes tightened one layer at a time. Then the great mirror wings unfolded into place. Piece by piece, the observatory transformed from its compact launch configuration into the largest space telescope ever constructed. Each successful deployment brought quiet celebration inside mission control. One step completed, then another, then another. Days became weeks. Finally, Webb reached its destination near L2. Yet another challenge remained. Although the mirror segments were precisely manufactured, they initially behaved like 18 separate telescopes, rather than one unified instrument. Engineers carefully adjusted each segment using microscopic actuators capable of moving the mirrors by distances measured in nanometers. Tiny corrections, again, until 18 separate reflections merged into one perfectly focused image. The telescope had opened its eyes. Then came the moment the world had been waiting for. In July 2022, the first full-color scientific images were released. Among them was Webb's first deep field. At first glance, it resembled countless previous photographs of the night sky. Look a little longer. Almost every point of light was not a star. It was an entire galaxy. Each galaxy contained billions or even hundreds of billions of stars. Some appeared as graceful spirals, others as glowing ellipses. Some were distorted into graceful arcs by gravitational lensing, where massive foreground galaxy clusters bent the light of even more distant galaxies behind them. The image covered only a tiny patch of sky, roughly the size of a grain of sand, held at arm's length. Yet within that tiny window, thousands of galaxies appeared. Some of their light had traveled for more than 13 billion years before finally reaching Webb's mirrors. For the first time, humanity was seeing extraordinary detail from an era astonishingly close to the beginning of cosmic history. Scientists celebrated the telescope's engineering success, but something else soon became clear. The universe was not behaving exactly as expected. Within months, Webb began finding galaxies that appeared larger, brighter, and more mature than existing models had predicted. Instead of gradually confirming decades of theory, the telescope began raising new questions. Questions that would reshape conversations throughout modern cosmology. Sometimes the greatest scientific breakthroughs do not come from proving our expectations correct. They begin when nature quietly reveals that reality is even more remarkable than we imagined. When the first images from the James Webb Space Telescope reached astronomers around the world, the excitement was impossible to ignore. Years of planning, engineering, and patient anticipation had finally given humanity a new window into the ancient universe. At first, many researchers expected Webb to confirm what decades of observations had already suggested. The earliest galaxies, they believed, would appear small, faint, irregular. These young systems would be the first building blocks from which today's magnificent spiral and elliptical galaxies gradually grew over billions of years. Instead, Webb began showing something unexpected. Some of the universe's earliest galaxies appeared surprisingly bright. Some appear remarkably massive, and several seemed far more mature than existing models had predicted. Rather than finding only cosmic infants, astronomers were suddenly looking at galaxies that seemed to have reached adolescence or even adulthood far earlier than anyone had imagined. To understand why this was such a surprise, it helps to remember what astronomers mean when they look deeper into space. Unlike ordinary travel, looking farther into the universe also means looking farther back in time. Light travels at a finite speed, about 300,000 kilometers every second. The sunlight warming Earth today left the sun approximately 8 minutes ago. The light from the Andromeda galaxy began its journey more than 2 million years ago. When Webb observes galaxies whose light has traveled for over 13 billion years, it is not seeing them as they are today. It is seeing them as they were when the universe itself was still remarkably young. This is why astronomers often describe Webb as a time machine. It does not travel through time. Instead, it collects ancient light that has been traveling toward us since the earliest chapters of cosmic history. According to the prevailing cosmological model, the first galaxies should have formed gradually. Small clouds of dark matter attracted ordinary gas. Hydrogen and helium cooled. Gravity slowly pulled material together. The first stars ignited. Tiny galaxies merged into larger galaxies. Over hundreds of millions, and eventually billions of years, repeated mergers built the giant galaxies we observe throughout the modern universe. This hierarchical picture had successfully explained many observations made by previous telescopes, yet Webb immediately began revealing galaxies that seemed to challenge this timeline. One of the first major observing programs was known as JWST, the JWST Advanced Deep Extragalactic Survey. Its purpose was straightforward: search deeper into the early universe than any previous telescope had ever reached. The survey soon identified galaxies existing only a few 100 million years after the Big Bang. That alone was remarkable, but their appearance proved even more surprising. Several contained far more stars than expected. Some displayed organized structures rather than chaotic fragments. Others appeared extraordinarily luminous, suggesting vigorous episodes of star formation occurring at astonishing speeds. Another major program, the Cosmic Evolution Early Release Science Survey, or SEERS, produced similarly intriguing results. Again and again, Webb uncovered galaxies whose estimated masses seemed unexpectedly large for such an early epoch. Scientists quickly realized they faced an important question: were these galaxies genuinely massive? Or were astronomers misunderstanding what Webb was seeing? In science, extraordinary observations require extraordinary care. The first possibility was that the galaxies only appeared heavier than they truly were. Young galaxies filled with brilliant, short-lived stars can shine much more brightly than older populations. Brightness alone does not always reveal total mass. If these galaxies experienced intense bursts of star formation, their luminosity might temporarily exaggerate their apparent size. Another possibility involved dust. Interstellar dust absorbs and scatters light in complex ways. Previous telescopes often struggled to see through dusty regions. Because Webb observes primarily in infrared wavelengths, it can penetrate much of this obscuring material. Some galaxies that once appeared faint and primitive suddenly revealed far richer internal structures. The improved observations forced astronomers to revisit earlier estimates. Yet even after accounting for these effects, many researchers concluded that at least some early galaxies truly had assembled astonishing amounts of mass within surprisingly short periods of cosmic time. The discussion soon expanded beyond individual galaxies. Perhaps galaxy formation itself had been more efficient than previously believed. Maybe the earliest clouds of gas cooled faster. Perhaps star formation proceeded more rapidly under the conditions of the young universe. Some theoretical models suggested that dense concentrations of cold gas could collapse with extraordinary efficiency, producing stars far more quickly than simulations had assumed. Other researchers examined the role of dark matter. Although invisible, dark matter provides the gravitational framework upon which galaxies form. If the earliest dark matter halos assembled sooner or grew faster than expected, ordinary matter might also have accumulated more rapidly. Computer simulations continue exploring these possibilities. Each new observation helps refine the models. Another important factor involves cosmic redshift. As the universe expands, light stretches toward longer wavelengths. Astronomers measure this stretching using a quantity known as redshift, often represented by the letter Z. Higher redshift corresponds to greater distance and earlier cosmic time. Some of Webb's most intriguing galaxies possess redshifts greater than 10. This means their light began traveling toward Earth when the universe was less than 500 million years old. Only a small fraction of its present age, of approximately 13.8 billion years. To appreciate how early this truly is, imagine compressing the entire history of the universe into a single calendar year. Earth would not appear until early September. Dinosaurs would arrive near Christmas. Human civilization would occupy only the final moments before midnight on December 31st. Yet Webb is observing galaxies that formed during the very first days of that cosmic calendar. No wonder astronomers were astonished to find systems already containing billions of stars. Of course, science does not change overnight. The discoveries did not overturn the Big Bang model, nor did they invalidate decades of cosmological research. Instead, they highlighted an essential strength of science itself. Good theories are not protected from new evidence. They are refined by it. Throughout history, improved instruments have repeatedly revealed complexities that earlier generations could not see. Galileo transformed astronomy with his telescope. Edwin Hubble revealed that the universe extends far beyond the Milky Way. Now James Webb is providing another leap forward, offering observations of unprecedented sensitivity and clarity. The universe is proving neither simpler nor stranger than science expected. Rather, it is richer, more detailed, more nuanced. Each unexpected galaxy becomes another piece of an immense cosmic puzzle. Some pieces fit comfortably into existing models. Others encourage entirely new questions. How rapidly could stars truly form? How efficiently did gas gather within young galaxies? Were the earliest galaxies fundamentally different from those that formed later? Or are we only beginning to understand the remarkable diversity of cosmic evolution? These questions remain active areas of research. New observations arrive every month. New simulations become increasingly sophisticated. The conversation continues, not because science is failing, but because discovery is succeeding. Every image Webb returns reminds us that nature is under no obligation to match our expectations. The universe simply reveals itself, one observation at a time. And as astronomers continue looking deeper into the ancient light, another mystery slowly comes into focus. Before there were galaxies filled with billions of stars, there had to be a time when no stars existed at all. A universe without starlight. A universe waiting for its very first sunrise. That is where our journey leads next. Long before the graceful spiral galaxies we see today, before planets circled their stars, before heavy elements filled the universe with the ingredients for mountains, oceans, and life itself, there was a time when none of these things existed. The universe was astonishingly simple. There were no forests, no worlds, no galaxies glowing across the heavens, not even a single star. It is difficult to imagine such a cosmos, because every night sky we have ever known is filled with light. Yet for millions of years after the Big Bang, the universe remained dark. Astronomers call this period the Cosmic Dark Ages. Despite its name, this era was not empty. Space was filled with enormous clouds of hydrogen and helium, the two lightest elements forged during the first few minutes after the Big Bang. These gases drifted quietly through an expanding universe, cooling gradually as space itself continued to stretch. There were no suns to illuminate these vast clouds, No galaxies to paint the heavens, only darkness. Yet beneath that silence, gravity was already at work. Tiny differences in density, almost unimaginably small, had been imprinted into the young universe. Some regions contained slightly more matter than others. Over millions of years, gravity amplified these tiny variations. Regions with a little more matter attracted even more matter. Clouds slowly became denser. Denser clouds attracted additional gas. The process was almost unimaginably patient. Nothing dramatic happened overnight. The universe was quietly preparing for its first dawn. Dark matter played an essential role during this period. Although it neither emits nor reflects light, dark matter exerts gravity. Astronomers believe it formed an invisible framework stretching across the cosmos. Ordinary hydrogen and helium gradually collected within these gravitational wells, creating increasingly dense clouds capable of collapsing under their own weight. Eventually, gravity won. As enormous clouds contracted, their centers became hotter and denser. Temperatures climbed into the millions of degrees. Pressure increased beyond anything found naturally on Earth. Then, for the first time since the Big Bang itself, nuclear fusion ignited. The first stars were born. Astronomers call these primordial objects population 3 stars. Despite the name, they actually represent the universe's first generation of stars. The numbering reflects historical terminology rather than chronological order. Unlike the Sun, these earliest stars contained almost nothing except hydrogen and helium. Elements such as carbon, oxygen, silicon, calcium, and iron did not yet exist. Even something as familiar as the oxygen we breathe had not been created. The first stars would change all of that. Because they formed from pristine gas, many researchers believe population 3 stars were dramatically different from most stars we observe today. Without heavier elements to help cool collapsing gas clouds, enormous amounts of material may have gathered before fusion began. As a result, many of these stars were probably extraordinarily massive. Some theoretical models suggest masses tens or even hundreds of times greater than our Sun. Massive stars live remarkably different lives from smaller ones. Our Sun is expected to shine for roughly 10 billion years. The largest primordial stars may have survived only a few million years. They lived brilliantly. They exhausted their nuclear fuel rapidly. Then they died in spectacular explosions. Yet those brief lives transformed the universe forever. Inside every star, nuclear fusion acts like a cosmic furnace. Hydrogen nuclei combine to form helium. Helium eventually fuses into carbon, carbon into oxygen. Progressively heavier elements continue forming deep within stellar interiors. The largest stars create silicon, sulfur, calcium, and finally, iron. Iron marks an important boundary. Fusion beyond iron no longer releases energy efficiently. When a massive star develops an iron core, gravity eventually overwhelms the pressure supporting it. The star collapses, then explodes. These explosions, known as supernovae, scatter newly created elements across interstellar space. Everything heavier than helium, every atom of oxygen in our lungs, calcium in our bones, silicon in rocks, and iron in our blood, was forged inside generations of stars that lived and died long before Earth existed. In that sense, the first stars became the universe's earliest architects. Without them, later generations of stars could never have formed planets rich in complex chemistry. Without those heavier elements, rocky worlds like Earth would not exist. The universe needed stars before it could build planets. It needed planets before life could emerge. The first stars quietly prepared the way for everything that followed. Yet finding these ancient pioneers remains one of astronomy's greatest challenges. No confirmed population 3 star has ever been observed directly. The reason is not surprising. If these stars were as massive as many models suggest, they lived only briefly before exploding. They disappeared billions of years ago. Today, astronomers search for their fingerprints rather than the stars themselves. One clue comes from chemical composition. Later generations of stars inherit the elements produced by earlier ones. By studying extremely ancient stars within our own Milky Way, stars containing remarkably small amounts of heavy elements, astronomers hope to reconstruct the conditions that existed shortly after the first stellar generation enriched the cosmos. Another clue comes from distant galaxies observed by the James Webb Space Telescope. Webb possesses extraordinary sensitivity to faint infrared light emitted more than 13 billion years ago. Its instruments can detect galaxies existing during the era when population 3 stars may still have been forming. Researchers carefully analyze the spectra of these galaxies. A spectrum separates light into its individual wavelengths, revealing subtle signatures produced by different chemical elements. If astronomers discover galaxies showing almost no evidence of heavier elements, they may have found environments containing truly primordial stellar populations. Several intriguing candidates have already emerged. Some galaxies exhibit unusually strong ultraviolet emission. Others appear chemically primitive compared with later galaxies. These observations do not yet prove the direct detection of population 3 stars, but they narrow the search considerably. Each new observing campaign brings astronomers closer to understanding the universe's first sunrise. The discoveries also remind us how interconnected cosmic history truly is. The earliest stars did far more than simply produce light. Their radiation began changing the very nature of the universe itself. For hundreds of millions of years, vast clouds of neutral hydrogen filled intergalactic space. As intense ultraviolet light poured outward from the first generations of stars and young galaxies, it gradually transformed those hydrogen atoms. The darkness did not disappear all at once. Instead, islands of light slowly expanded through an ocean of cosmic fog. Tiny pockets of illumination grew larger. They merged with neighboring regions. Little by little, the universe became transparent. This transformation would reshape the cosmos on the grandest possible scale. The first stars had ended the cosmic dark ages, but their greatest influence was only beginning. Their light would eventually change the entire universe, allowing it to become the clear and luminous cosmos that Webb now explores across billions of years of history. That remarkable transformation is known as the epoch of reionization, one of the most important chapters in the story of cosmic evolution. It is there that our journey continues next. If you could have traveled through the universe a few 100 million years after the Big Bang, you would have encountered a cosmos unlike the one we know today. There would have been stars. There would have been young galaxies. Yet if you looked across vast distances, your view would not have stretched endlessly into space. Instead, much of the universe would have appeared hidden behind an immense cosmic fog. This fog was not made of water droplets like the mist that gathers over a quiet lake before sunrise. It was made of one of the simplest substances in existence: neutral hydrogen. Hydrogen is the most abundant element in the universe. Every hydrogen atom consists of a single proton with a single electron bound to it. During the cosmic dark ages, after the universe had cooled enough for atoms to form, enormous quantities of neutral hydrogen filled intergalactic space. Although invisible to our eyes, this gas had an important property. It readily absorbed energetic ultraviolet light. As a result, light from the earliest stars could not travel freely across the cosmos. Instead, much of it was absorbed almost as soon as it was emitted. The young universe was filled with light sources, yet much of that light remained trapped within an opaque sea of hydrogen. Astronomers call this remarkable chapter of cosmic history the epoch of reionization. It represents one of the greatest transformations the universe has ever experienced. To understand why, it helps to distinguish between two forms of hydrogen. When hydrogen contains both its proton and electron, it is electrically neutral. But if enough energy removes the electron, the atom becomes ionized. An ionized hydrogen atom no longer absorbs ultraviolet light in the same way. Instead, light can travel much farther through the surrounding space. This simple change, from neutral hydrogen to ionized hydrogen, gradually transformed the entire universe from opaque to transparent. But how did that transformation begin? The answer lies with the first generations of stars. Massive young stars produce enormous amounts of ultraviolet radiation. Each photon capable of escaping its parent galaxy carried enough energy to strip electrons away from neutral hydrogen atoms. Around every young galaxy, a small bubble of ionized gas began to grow. At first, these bubbles were tiny. They surrounded individual star-forming regions, like islands of light, floating within an immense cosmic ocean. As more stars formed, the bubbles expanded. Neighboring galaxies created their own regions of ionization. Slowly, patiently, these expanding islands began touching one another. Small bubbles merged into larger ones. Large bubbles merged into enormous cosmic regions. Over hundreds of millions of years, the fog steadily retreated. There was no single moment when darkness suddenly vanished. Instead, the universe awakened gradually. Light advanced little by little across unimaginable distances. This quiet transformation changed everything that followed. Once intergalactic space became largely transparent, light from distant galaxies could travel freely across billions of light years. Without reionization, many of the galaxies that James Webb observes today would remain hidden behind vast curtains of neutral hydrogen. In a very real sense, Webb is possible because the early universe became transparent. One of the great questions facing modern astronomy is identifying exactly which objects drove this enormous transformation. For many years, astronomers suspected that extremely bright quasars, galaxies powered by actively feeding supermassive black holes, might have provided most of the necessary ultraviolet radiation. Quasars certainly emit tremendous amounts of energy. Some outshine entire galaxies. However, as observations improved, researchers realized that quasars were probably too rare during the earliest stages of cosmic history to account for the entire process. Attention gradually shifted towards something much smaller: young dwarf galaxies. Although individually faint, these galaxies were incredibly numerous. Each contained vigorous episodes of star formation. Collectively, millions of these small systems may have produced enough ultraviolet light to ionize the universe over time. The James Webb Space Telescope has become one of the most powerful tools for investigating this possibility. Because Webb observes extremely distant galaxies in infrared wavelengths, it can detect objects whose visible light has been stretched far into the infrared by cosmic expansion. Many of these galaxies existed precisely during the epoch of reionization. Their light carries valuable clues about conditions in the early universe. Astronomers carefully examine the spectra of these galaxies. Certain spectral features reveal whether surrounding hydrogen remains mostly neutral or largely ionized. Other measurements estimate how efficiently ultraviolet radiation escaped from young galaxies into intergalactic space. This quantity is known as the escape fraction. Not every ultraviolet photon leaves its galaxy. Many are absorbed by gas and dust before they can escape. Determining how much radiation actually reached intergalactic space is essential for understanding how reionization unfolded. Webb's observations suggest that at least some early galaxies may have allowed far more ultraviolet radiation to escape than many previous models predicted. If confirmed across larger samples, these findings strengthen the idea that countless modest galaxies, rather than only rare quasars, collectively transformed the young universe. The picture emerging from Webb is both elegant and profound. No single galaxy illuminated the cosmos. No solitary event ended the cosmic dark ages. Instead, innumerable small sources of light worked together. Across hundreds of millions of years, generation after generation of young stars quietly reshaped the universe. This gradual cooperation reflects one of nature's recurring patterns. Great transformations often arise not from one extraordinary event, but from countless ordinary processes unfolding over immense spans of time. Astronomers continue refining the timeline. Current evidence suggests that reionization began perhaps 200 to 300 million years after the Big Bang and continued until roughly 1 billion years after the universe's birth. Even these numbers remain active areas of research. Every new Webb observation improves the picture. Every newly discovered galaxy fills another gap in the timeline. Some observations have even revealed surprisingly bright galaxies existing earlier than expected. If these systems form stars more efficiently than current models assume, they may have contributed significantly to reionization. Others appear chemically primitive, offering glimpses into environments where stellar populations still resembled the universe's earliest generations. As the data continue accumulating, astronomers are gradually replacing broad theories with increasingly detailed histories. The universe is revealing not only when reionization occurred, but how. Perhaps the most beautiful aspect of this story is its patience. Nothing happened suddenly. The universe did not rush. For hundreds of millions of years, light slowly overcame darkness. Tiny galaxies, almost invisible across cosmic distances, quietly altered the largest structures in existence. Today, more than 13 billion years later, the ancient photons released during that remarkable era continue their journey. Some eventually arrive at the golden mirrors of the James Webb Space Telescope. Others travel onward through space, still carrying news from an age when the first galaxies were transforming the cosmos. Yet even as astronomers reconstruct this great awakening, another mystery grows more puzzling. Among those early galaxies, Webb has uncovered objects of extraordinary power. Some contain black holes so massive that their existence seems almost impossible within the available time. How these giants formed so quickly remains one of the greatest unanswered questions in modern cosmology. That mystery awaits us next. Among all the discoveries made by the James Webb Space Telescope, few have surprised astronomers more than the appearance of enormous black holes in the earliest chapters of cosmic history. These are not the relatively modest black holes left behind when massive stars collapse. Those stellar black holes usually contain a few times, or perhaps a few dozen times, the mass of our Sun. The objects Webb is helping astronomers study belong to an entirely different category. They are supermassive black holes. Some contain millions, others contain billions, even tens of billions of times the mass of the Sun. Today, nearly every large galaxy appears to harbor one at its center. Our own Milky Way contains a supermassive black hole, known as Sagittarius A, whose mass is about 4 million suns. Although enormous by human standards, it is relatively modest compared with some of the giants discovered elsewhere in the universe. For many years, astronomers believed these cosmic titans required billions of years to grow. The idea seemed reasonable. A black hole gains mass by pulling in surrounding gas, dust, stars, and occasionally even other black holes. This process, called accretion, is powerful but not unlimited. As matter spirals inward, it becomes intensely hot. The resulting radiation pushes outward against additional infalling material, naturally limiting how quickly the black hole can continue feeding. Because of this balance, physicists calculate an approximate maximum long-term growth rate known as the Eddington limit. If a black hole grows steadily near this limit, reaching billions of solar masses should require an immense amount of time. That expectation fit comfortably within existing models. Then Webb began looking farther back into the universe. Some of the earliest galaxies revealed extraordinarily bright central regions. These brilliant objects are known as active galactic nuclei, or AGNs. When a supermassive black hole rapidly consumes surrounding material, the accretion disk surrounding it becomes one of the brightest objects in the cosmos. In fact, the light produced by matter falling toward a black hole can outshine every star in its host galaxy combined. When viewed across enormous distances, these brilliant nuclei are often classified as quasars. Quasars had already been known for decades. Even before Webb, astronomers had identified quasars existing less than 1 billion years after the Big Bang. These discoveries were already challenging enough. Now Webb is extending the search even earlier. Some observations suggest actively growing black holes were already present only a few 100 million years after the universe began. This raises an obvious question. How could something so massive grow so quickly? Imagine planting an acorn in the morning and returning that evening to find a towering forest. Even if the conditions were ideal, the available time would simply seem too short. That is the puzzle confronting astronomers. The problem is not that black holes exist. The problem is their remarkable speed of growth. To explain these observations, scientists are exploring several possibilities. One idea begins with the deaths of the first massive stars. If population 3 stars were hundreds of times more massive than the Sun, some may have collapsed directly into relatively large black holes. These seed black holes could then begin growing by accreting gas from their surroundings. Over time, repeated mergers and continued feeding might eventually produce supermassive black holes. This remains one plausible pathway. However, many calculations suggest it may still be difficult to reach billions of solar masses within only a few 100 million years. Another possibility is known as the direct collapse model. Instead of beginning with an ordinary star, enormous clouds of primordial gas might collapse almost directly into a black hole. Under very specific conditions, cooling mechanisms that normally trigger star formation could be suppressed. Rather than fragmenting into many stars, an immense cloud might continue collapsing until it forms a single extremely massive object. Such an object could quickly become a black hole, containing 100,000 or even 1 million solar masses from the very beginning. Starting with a much larger seed dramatically reduces the time required to produce the giants Webb is observing. Researchers continue investigating whether the necessary conditions occurred frequently enough in the young universe. A third possibility involves unusually rapid growth. Perhaps early black holes occasionally accreted matter faster than the traditional Eddington limit predicts. Certain theoretical models suggest that under exceptional circumstances, gas can flow inward so efficiently that black holes temporarily exceed this apparent limit. If such episodes occurred repeatedly during the universe's earliest epochs, they could help explain unexpectedly massive black holes. Computer simulations continue exploring this possibility. Some scientists are also examining the role of dense stellar clusters. In crowded environments, repeated collisions between massive stars could produce exceptionally large intermediate black holes. These objects might then merge with others while continuing to accrete gas, eventually reaching supermassive scales. No single explanation has yet emerged as the definitive answer. Each model reproduces some observations while leaving other questions unresolved. This is precisely how scientific investigation progresses. Observations inspire hypotheses. Hypotheses generate predictions. New observations test those predictions. Gradually, understanding improves. One of Webb's most valuable contributions lies not merely in discovering more black holes, but in revealing the environment surrounding them. Astronomers are learning that galaxies and their central black holes appear deeply connected. The growth of one influences the evolution of the other. As gas falls toward a black hole, enormous amounts of energy are released. Powerful jets and intense radiation can heat surrounding gas, slowing future star formation. Conversely, dense reservoirs of cold gas feeding vigorous star formation may also nourish the central black hole. This complex relationship is often called galaxy-black hole coevolution. Rather than evolving independently, galaxies and their central black holes appear to shape one another throughout cosmic history. Webb's remarkable sensitivity allows astronomers to study this relationship at much earlier times than ever before. Some surprisingly small galaxies already appear to host actively growing black holes. Others contain black holes whose masses seem unexpectedly large compared with the surrounding stellar population. These discoveries suggest that black hole growth may have begun almost simultaneously with galaxy formation itself. Exactly which process came first remains uncertain. Did young galaxies build enormous black holes? Or did rapidly growing black holes help organize the formation of their host galaxies? Perhaps both processes unfolded together, each influencing the other across hundreds of millions of years. the answers remain hidden within ancient light that has traveled more than 13 billion years before reaching Webb's mirrors. Every new observing campaign provides additional pieces of the puzzle. Some earlier interpretations have already been refined as improved measurements became available. Several candidate galaxies initially believed to contain extraordinary masses were later found to be somewhat less extreme after more detailed spectroscopic observations. This careful process illustrates an important strength of astronomy. Extraordinary discoveries are continually tested, refined, and re-evaluated as better data arrive. The goal is not dramatic headlines. The goal is an increasingly accurate understanding of reality. For now, the mystery remains one of the most fascinating in modern cosmology. The earliest universe seems to have produced giant black holes with astonishing efficiency. Whether through direct collapse, unusually rapid accretion, massive primordial seeds, repeated mergers, or perhaps a combination of several processes, nature found pathways that scientists are only beginning to understand. Yet even these immense black holes represent only part of a much larger story. They do not exist in isolation. They are woven into an extraordinary cosmic architecture stretching across hundreds of millions of light years. An architecture shaped not only by visible galaxies, but by an invisible framework that binds the universe together. To understand that grand design, we must step back even farther, beyond individual galaxies, beyond black holes, toward the immense structure astronomers call the cosmic web. If we could step far beyond the Milky Way and continue traveling outward, not for thousands, but for hundreds of millions of light years, the universe would begin to look very different. From Earth, galaxies often appear scattered across the night sky almost at random. Some seem isolated, others gather in small groups. At first glance, there appears to be little overall pattern. Yet, as astronomers gradually mapped larger and larger regions of the universe, an extraordinary picture began to emerge. Galaxies are not distributed randomly. Instead, they form an immense network stretching across the observable cosmos. This structure is known as the cosmic web. Imagine morning dew collecting upon the strands of an enormous spider's web. The droplets are brightest where multiple strands meet. Long, delicate filaments connect one intersection to another. Between them lie wide, empty spaces. On the largest scales currently observable, the universe appears remarkably similar. Galaxies cluster along gigantic filaments. Massive galaxy clusters occupy the intersections. Immense regions known as cosmic voids contain relatively few galaxies at all. Some of these voids stretch across hundreds of millions of light years. The cosmic web is the largest known structure in nature, yet most of it cannot be seen directly. The reason lies in one of modern astronomy's greatest mysteries: dark matter. Unlike ordinary matter, dark matter neither emits light nor reflects it. No telescope has ever photographed dark matter itself. Astronomers infer its presence through gravity. Galaxies rotate faster than visible matter alone can explain. Galaxy clusters bend light more strongly than their luminous mass predicts. The large-scale arrangement of galaxies also points toward an invisible gravitational framework. Current evidence suggests that approximately 85% of all matter in the universe exists in the form of dark matter. Although its true nature remains unknown, its influence is unmistakable. Long before the first stars ignited, dark matter had already begun shaping the universe. After the Big Bang, tiny fluctuations in density gradually grew through gravity. Dark matter, unaffected by radiation in the way ordinary matter was, collapsed into vast halos and interconnected filaments. Ordinary hydrogen and helium later flowed into these invisible structures. Where dark matter gathered, galaxies eventually formed. In this way, dark matter became the hidden scaffolding upon which the visible universe was built. The galaxies we admire today may be thought of as luminous tracers, revealing an underlying architecture that remains invisible. The James Webb Space Telescope is helping astronomers explore this architecture in unprecedented detail. Although Webb cannot see dark matter directly, it observes the galaxies whose positions reveal the structure surrounding them. Because Webb detects extremely distant galaxies with extraordinary sensitivity, researchers can examine how these ancient systems were arranged when the universe was still young. Were the earliest galaxies already gathering along filaments? How rapidly did large-scale structure emerge? How did galaxy clusters begin assembling? These questions lie at the heart of several ambitious observing programs. One of them is the Cosmos Webb Survey. Covering one of the largest areas ever observed by Webb, this program seeks to map hundreds of thousands of galaxies across enormous spans of cosmic time. Rather than focusing on only a tiny region of the sky, Cosmos Webb examines a broad section, allowing astronomers to study how galaxies cluster together over billions of years. By comparing nearby galaxies with extremely distant ones, researchers can trace the gradual growth of cosmic structure from the early universe until today. Another remarkable program is the Uncover Survey. Its name reflects one of astronomy's most powerful natural phenomena, gravitational lensing. More than a century ago, Albert Einstein's theory of general relativity predicted that gravity bends space itself. Light traveling through curved space follows those curves. As a result, massive galaxy clusters can bend and magnify the light from galaxies lying far behind them. Nature creates its own telescope. When Webb observes one of these enormous galaxy clusters, the cluster's gravity acts like a giant magnifying glass. Tiny galaxies that would otherwise remain invisible become bright enough to study. Nature creates its own telescope. Sometimes astronomers observe graceful arcs surrounding foreground clusters. These arcs are not strange new galaxies. They are distorted images of much more distant galaxies, whose light has been stretched by gravity during its journey across billions of light years. Through gravitational lensing, Webb effectively extends its vision even farther into the ancient universe. This combination of advanced technology and natural gravitational lenses has allowed astronomers to detect galaxies that formed remarkably early in cosmic history. Some of these tiny systems may represent important building blocks from which larger galaxies eventually grew. Others provide clues about how matter accumulated along the cosmic web's invisible filaments. The picture continues becoming richer with every observing campaign. Computer simulations help place these observations into a broader framework. Modern cosmological simulations begin shortly after the Big Bang, with tiny fluctuations measured in the cosmic microwave background. Gravity then acts upon these initial conditions over billions of years. Gradually, delicate filaments emerge. Galaxy clusters grow where filaments intersect. Large voids expand between them. When astronomers compare these simulations with Webb's observations, they often find remarkable agreement on the universe's largest scales. At the same time, Webb reveals details that encourage further refinement. The distribution of early galaxies, the timing of cluster formation, the efficiency of star formation within different environments. Each new observation improves our understanding of how the cosmic web evolved. Perhaps the most striking aspect of the cosmic web is its scale. Individual galaxies already seem unimaginably large. The Milky Way spans roughly 100,000 light-years, yet galaxy clusters contain hundreds or even thousands of galaxies. Filaments connect clusters across distances exceeding 100 million light-years. The observable universe itself extends for approximately 93 billion light-years in diameter. Against such immense dimensions, even the largest galaxies become tiny points within a much greater design. And still, the web continues beyond everything we can presently observe. Or does it? This question naturally leads to another profound mystery. When astronomers speak of the observable universe, they are making a careful distinction. It is not necessarily the entire universe. It is simply the portion whose light has had enough time to reach us since the beginning of cosmic expansion. Beyond that limit may lie countless additional galaxies, additional filaments, additional clusters, Perhaps structures even grander than those we can presently detect, or perhaps something entirely unexpected. The James Webb Space Telescope is revealing the universe with extraordinary clarity. Yet even Webb cannot see infinitely far. Every telescope, no matter how powerful, eventually encounters the fundamental limits imposed by physics itself. To understand those limits, we must explore one final frontier, not the edge of space, but the edge of what light itself can reveal. When we look into the night sky, it is natural to imagine the universe stretching endlessly in every direction. The stars seem countless, the galaxies appear without number. The farther our telescopes can see, the more distant worlds they reveal. Yet even the James Webb Space Telescope, extraordinary as it is, cannot observe everything. Not because its mirrors are too small, not because its instruments lack precision, but because the universe itself places a fundamental limit on what any telescope can ever observe. Astronomers call this boundary the observable universe. The phrase is carefully chosen. It does not describe the entire universe. It describes only the portion from which light has had enough time to reach us since the beginning of cosmic expansion. Everything we have ever seen, every star, every galaxy, every nebula, every quasar, exists within that observable region. Beyond it may lie vastly more, but no light from those regions has yet arrived. To understand why, we must begin with one of nature's most fundamental constants, the speed of light. Light travels at approximately 300,000 kilometers every second. Within a single second, it could circle Earth more than 7 times. Across human scales, that speed feels almost instantaneous. Across cosmic distances, however, even light requires immense amounts of time. Sunlight reaches Earth in about 8 minutes. Light from Jupiter takes roughly 45 minutes. The nearest star beyond our Sun sends light that travels for more than 4 years before arriving here. The Andromeda Galaxy appears as it existed approximately 2.5 million years ago. The most distant galaxies observed by Webb emitted their light over 13 billion years ago. Looking farther into space truly means looking farther back through time. Yet another subtle effect makes the universe even more fascinating. Space itself is expanding. This discovery transformed cosmology during the 20th century. Galaxies are generally not racing outward through empty space like fragments from an explosion. Instead, the fabric of space itself is stretching. Imagine placing dots upon the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot. No single dot occupies the center of expansion. The distances simply increase as the surface grows. Although this analogy has limitations, it illustrates an important principle. As space expands, light traveling through it is stretched as well. Its wavelength becomes longer. Its color gradually shifts toward the red end of the spectrum. Astronomers call this cosmological redshift. The greater the redshift, the farther the light has traveled, and the earlier in cosmic history it was emitted. This is why the James Webb Space Telescope specializes in infrared astronomy. Many of the universe's earliest galaxies originally emitted visible and ultraviolet light. After more than 13 billion years of cosmic expansion, those wavelengths have stretched deep into the infrared. Without infrared instruments, much of the early universe would remain invisible. Yet there is another limit that no telescope can overcome. Long before the first stars formed, the universe was filled with an intensely hot plasma. Electrons and atomic nuclei moved freely rather than combining into neutral atoms. Photons constantly scattered from one charged particle to another. Light could not travel freely across space. The universe was opaque. Only after approximately 380,000 years did temperatures fall enough for electrons and nuclei to combine into neutral hydrogen. Astronomers call this event recombination. Once neutral atoms formed, photons finally escaped. Many of those ancient photons continue traveling today. We detect them as the cosmic microwave background, often abbreviated as the CMB. This faint glow fills the universe in every direction. It represents the oldest light we can directly observe. No ordinary telescope, not Hubble, not Webb, nor any future optical observatory, can see farther back using light alone. The universe before recombination remains hidden behind that primordial plasma. This is one of the most important limits in observational astronomy. When people ask whether Webb can photograph the Big Bang itself, the answer is no. Not because Webb lacks sufficient power, because light from earlier times simply cannot reach us. The universe had not yet become transparent. Light itself was trapped. To explore even earlier moments, scientists rely upon other methods. They study subtle patterns preserved within the cosmic microwave background. They search for primordial gravitational waves. They construct theoretical models describing inflation and the earliest fractions of a second after the Big Bang. These investigations continue today. Some questions remain open. One of them concerns cosmic inflation. According to the leading model, the universe experienced an extraordinarily rapid expansion during an unimaginably brief instant after the Big Bang. Regions once microscopically close became separated across enormous distances. Inflation helps explain why the observable universe appears remarkably uniform on large scales. It also provides a mechanism for generating the tiny density fluctuations that eventually grew into galaxies and clusters. Although inflation successfully explains many observations, astronomers continue investigating exactly how it occurred. Webb cannot observe inflation directly. Its effects happened long before light could travel freely. Still, Webb's measurements of the earliest galaxies help test predictions made by inflationary cosmology. Every ancient galaxy becomes another piece of evidence within a much larger scientific picture. Another concept often causes confusion: the particle horizon. This horizon marks the greatest distance from which light has had time to reach us since the beginning of cosmic history. Because the universe expanded while that light traveled, the most distant observable regions now lie roughly 46.5 billion light-years away in every direction. This is why the observable universe measures approximately 93 billion light-years across, despite being only about 13.8 billion years old. Expansion changes the geometry of distance. There is also the cosmic event horizon. Unlike the particle horizon, the event horizon concerns the future. Because cosmic expansion is accelerating, there are galaxies whose present light will never reach us, no matter how long humanity waits. They are receding because space itself expands ever more rapidly. Their future light is effectively carried away faster than it can bridge the growing distance. In that sense, some parts of today's universe are already permanently beyond future observation. This realization can feel almost poetic. The universe contains regions forever hidden from us, not because they do not exist, not because science has failed, simply because the laws of nature establish boundaries. Every generation has encountered horizons. Ancient sailors reached the edge of familiar seas. Explorers crossed unknown continents. Astronomers extended vision beyond the solar system, beyond the Milky Way, beyond nearby galaxies. Now the James Webb Space Telescope has carried our sight astonishingly close to the beginning of cosmic history. Yet the horizon remains. Beyond it may lie countless additional galaxies. Perhaps the universe continues forever. Perhaps it curves back upon itself in ways we do not yet understand. Perhaps reality is larger and stranger than even our greatest theories imagine. For now, those questions remain beautifully unanswered, and perhaps that is one of the greatest gifts the universe offers. Not certainty, but wonder. As remarkable as Webb's discoveries have been, they have not completed humanity's understanding of the cosmos. Instead, they have illuminated new mysteries waiting just beyond the limits of our vision. Those mysteries will guide the final chapter of our journey. For thousands of years, every great leap in astronomy has followed the same pattern. A new instrument extends our vision. The universe appears clearer than ever before. old questions find answers, and almost immediately, new questions emerge. The James Webb Space Telescope has continued this remarkable tradition. It has shown us galaxies that formed earlier than expected. It has revealed ancient black holes, whose origins remain uncertain. It has allowed us to peer into the era when the first stars illuminated the cosmos. Yet perhaps Webb's greatest achievement is not answering every mystery. It is showing us how much remains unknown. That realization is not a weakness of science. It is one of its greatest strengths. Every discovery becomes the beginning of another journey. One of the largest remaining mysteries concerns dark matter. Throughout this documentary, we have seen how dark matter appears to shape galaxies and the immense cosmic web. Its gravitational influence is measured repeatedly. Without it, galaxies would rotate differently. Clusters would not remain bound together. Large-scale cosmic structures would be difficult to explain. Yet after decades of research, no experiment has directly identified the particle or particles that compose dark matter. Astronomers know what dark matter does. They do not yet know what it is. Some researchers propose entirely new elementary particles. Others explore modifications to our understanding of gravity itself. Experiments deep underground continue searching for rare interactions between dark matter and ordinary matter. Powerful particle accelerators seek possible candidates. Space observatories search for indirect evidence across the universe. So far, the mystery remains. Closely connected is another even larger puzzle: dark energy. In 1998, astronomers made a surprising discovery. The expansion of the universe is not slowing under gravity alone. Instead, it is accelerating. Galaxies continue moving farther apart at an ever-increasing rate. Something appears to be driving this acceleration. Whatever that something is, astronomers call it dark energy. Unlike dark matter, which pulls through gravity, dark energy seems to influence the expansion of space itself. Current observations suggest that approximately 70% of the universe's total energy content exists in this mysterious form. Ordinary matter, the stars, planets, gas clouds, and galaxies we see, accounts for only a small fraction of the whole. In other words, most of the universe consists of components whose fundamental nature remains unknown. The James Webb Space Telescope was not specifically designed to solve either mystery, yet its precise observations of distant galaxies provide valuable information. By measuring how galaxies formed across billions of years, Webb helps astronomers test competing cosmological models. Some predictions become stronger. Others require revision. Each observation quietly narrows the possibilities. Another enduring question concerns the universe's first generation of stars. Throughout this journey, we have spoken about population 3 stars, the hypothetical pioneers that transformed a dark universe into one filled with light. Although Webb has identified promising candidate galaxies where these stars may once have existed, no confirmed direct observation has yet been made. Some astronomers believe the first definitive evidence may come during future Webb observing campaigns. Others suggest that entirely new observatories will eventually be required. The search continues. The same is true for the earliest black holes. Were they born from direct collapse? Did unusually massive primordial stars produce large seeds? Did repeated mergers accelerate their growth? Or did several different mechanisms operate simultaneously throughout the young universe? Each new observation provides another clue. Each new spectrum removes one possibility while strengthening another. Rarely does science advance through a single dramatic revelation. More often, understanding grows quietly, one carefully measured observation at a time. Beyond these questions lies an even deeper one. Why does the universe possess the particular laws that it does? The strengths of gravity, electromagnetism, and the nuclear forces appear finely balanced. If some of these values differed even slightly, stars might never have formed. Complex chemistry could have been impossible. Long-lived galaxies might never have existed. Physicists continue exploring whether these apparent balances arise from deeper physical principles, from cosmic inflation, from quantum processes, or from possibilities not yet imagined. At present, no consensus exists. Another profound question concerns the overall shape of the universe. Is space truly infinite? Or is it finite yet without an edge, curving back upon itself in higher dimensions, much as Earth's surface curves, without presenting travelers with a boundary? Current observations suggest that the observable universe is remarkably close to spatially flat. Yet whether the entire universe extends infinitely beyond our horizon remains unknown. Our observable region may represent only a tiny portion of a much larger reality. Some theoretical models even allow for the possibility of multiple universes arising under particular conditions during cosmic inflation. This idea, often called the multiverse hypothesis, remains speculative. At present, there is no direct observational evidence confirming its existence. It illustrates an important distinction within science. Some ideas are strongly supported by observation, others remain mathematical possibilities awaiting future tests. Good science carefully distinguishes between the two. The James Webb Space Telescope continues contributing to this careful process. Every observing cycle expands enormous public archives, filled with measurements available to researchers throughout the world. Thousands of astronomers examine these data from different perspectives. Some study galaxy evolution, others investigate star formation. Some analyze planetary atmospheres around distant worlds. Others search for the earliest quasars or the faintest dwarf galaxies. Each research group adds another small piece to humanity's growing understanding of the cosmos. This collaborative effort may be one of Webb's greatest legacies. Its discoveries belong not to one nation, one university, or one generation. They become part of a shared scientific story spanning the entire world. Future telescopes will almost certainly surpass Webb's capabilities. New observatories may directly detect population 3 stars. They may reveal the earliest stages of black hole formation. They may study the atmospheres of Earth-like planets with extraordinary precision. They may answer questions that today seem almost impossible. And those future discoveries will almost certainly produce new mysteries of their own. That has always been the rhythm of exploration. The horizon moves outward. Wonder remains. Perhaps this is the quiet lesson the James Webb Space Telescope offers us. The universe is not becoming smaller as we learn more. It is becoming deeper, richer, more intricate. Every answer reveals another layer. Every observation reminds us that reality is more beautiful than our expectations. From the first light after the cosmic dark ages, to galaxies that assembled with astonishing speed, to supermassive black holes that challenge current theories, to the invisible web connecting billions of galaxies, to the distant horizon beyond which no light has yet arrived. The universe invites both confidence and humility. Confidence because careful observation allows us to understand extraordinary truths. Humility because every generation discovers that there is still more to learn. As the golden mirrors of the James Webb Space Telescope continue collecting ancient photons, they are doing far more than photographing distant galaxies. They are extending one of humanity's oldest conversations, a conversation that began when our earliest ancestors looked upward into the night sky and wondered what lay beyond the stars. Today, we still ask that same question. Only now, we ask it with mirrors of gold, instruments cooled almost to absolute zero, and light that has traveled for more than 13 billion years. The answers continue to arrive, quietly, one photon at a time.